All right, boosting. Okay. So you've noticed that I go on and on and on about how awesome linear functions are to learn. On and on. And so and I keep saying, well, if you have something that's nonlinear that you want to learn, just put some good features on it, and then it's going to be linear. But what happens if you don't know the good features off the top of your head, right? I mean, shouldn't the computer figure some part of this out for us? So my answer to that is, okay, use boosting. Boosting is a way of taking a learner it's called a weak learner, like it's getting more than 51% of the answers correct. Like it's a little bit better than random. But it's not necessarily doing awesome. And it's a way of making it even better by actually combining multiple weak learners together. So if you learn like 10 really crappy classifiers, you can combine them with boosting. And in fact, boosting is a way of saying what 10 crappy classifiers you should learn in such a way that they will combine well together and give you better performance than you would have gotten from any of the individuals on their own.
Does this also work with 10 amazing classifiers?
Yeah, it'll actually work with anything. That's one of the amazing things about boosting is that boosting is a process that you run, and every iteration of boosting, you add another classifier to your little cabal that you're making. And if you continue this process forever, you will reach 100% accuracy on your training data. Guaranteed. Which is kind of a scary thought. Now, notice I said on your training data, it's totally not guaranteed that you're going to be generalizing well at this point. Gee, we need to somehow stop at some point. How do we figure that out? Cross-validation. So boosting. These methods are also called ensemble learners because you end up with this little committee of classifiers that they all weigh in on what they think about some new example, and they vote on whether it should be classified, whether it should be a positive example or a negative example. It's just amazing. Let me show you a brief example, and then I'll do the algorithm. The algorithm is really, it's like fits on one slide. Let me show you, though. There's somebody made a nice app. Let's see. Boop, boop, boop. So those are positive examples. And I thought right-click was negative examples. Am I wrong? Is it shift-click? Uh-oh. Click to add sample points. Oh, whoops, this is the wrong applet. No wonder it's not doing what I thought. Crap. All right, this is the applet from last time. Sorry. Here we go. Boosting. Boost. There we go. Okay. Yes, please run. Okay. So I'm going to make a data set that is totally not linearly learnable. So I think we would all agree, come on, Java, you can do it. There we are. Here are some points that are in one class. And here are some points in another class. Now that's very learnable by a linear function, right? We're just going to learn this function. The decision boundary is going to be right here. We're going to learn a plane that's like, I don't know which of these are positive and which are negative. Let's say that's negative and this is positive. So we're going to learn a plane that goes up out of the board as it comes down. So these are going to be greater than 0 if we want to use 0 as our threshold. And those are going to be less than 0 or less than 0.5 or whatever we're going to use. So if you ran linear regression, you have two input variables. So you're learning a plane. and it's going to cut through the decision boundary is going to be right through here. So that's very linearly learnable. So, but now I'm going to make this function evil. You silly computer. I'm going to thwart you. Okay. Good luck learning that with a linear function. Sucks to be you. Okay, does everyone see why that's a really hard function to learn with a line? Okay, so the way boosting works. Okay, first actually it wants us to split it into training and test data. So we'll go ka-chink. So that's now we have training and test, and now we're going to learn a linear classifier. Pa-chink. Please work, applet. Okay, so that's what it learned. So it learned a decision boundary here. So that's actually pretty accurate. So, I mean, these are all negative examples, and these are positive examples. So that's okay, but we're misclassifying all of these folks, so that's not so good. So now, what boosting does is it says, oh, crap, we got all these guys wrong. Let's pay more attention to them. And it weights them. It weights these guys more. And then learns another classifier on the same data. But the idea is pay more attention to those guys. So it learns another linear classifier that says, oh, that's negative. All this is positive. And it gets a couple guys wrong, but it gets these guys correct again. And now we're heavily weighting these folks because they were wrong both times. So now, what do you think it's going to learn now? Probably something either through here or through here. That's my guess. Ka-ching, yes. Ka-ching, yes. Ka-ching. We learn again and again. It learns each one of these steps through. We're learning a classifier. And this blue line here is the error on the training data of the complete ensemble of classifiers. And this green line here is error on the held out test set. And you can see our training error is extremely low. And in fact, yeah, if I keep running this, well, is our test error going to go down?
It seems to be registering as 0. You did 10 steps too.
Yeah. Anyway, it did pretty well in the end. We classified most of these guys correctly. Okay, so what happened here? What exactly is the algorithm that's happening in boosting? How does it work? You can see it has to do with learning multiple classifiers, and it can end up learning nonlinear things out of linear classifiers, which is amazing. We have n training examples. We have a weak learner, L. Now, there are two conditions on this learner. One is it has to be okay. It's at least got to get like 51% right. It can't be totally bad, like just guess randomly. That's not going to work. It has to be okay. And it has to handle weighted examples. There has to be some way of telling this learning algorithm, pay more attention to these guys. Like these guys are 1.5 times as important as these guys to get right. You have to have some way of doing that. So you can imagine with K and N, like you could overrepresent the ones you really cared about getting right. With naive Bayes, with linear regression, it's trivial to weight them. Just when you're doing an update, you like try harder to get those ones right. You increase the learning rate for those examples. For naive Bayes, you can increase the counts associated with those examples. So it's not too hard to achieve this. So these are actually very weak conditions. So we start off where all the training examples have the same weight. They're all equally important. And then we go into our loop. And the first thing we do is we call the learner. And we get back a classifier. Call it hypothesis T. So hypothesis for T. T is actually now 1. So we have H1. Now we go and we look at the probability that something got misclassified by this new classifier. If it's 0, we're done. Score. Get out of here. We're through. Otherwise, calculate this magical number, alpha, and I think I have a plot of alpha on the next slide. It helps if I turn this on, I guess. Alpha, yeah. So as the misclassification penalty, as the probability of misclassification goes up, then this number alpha goes down. When at 0.5, the weight is 0. If you're equally likely to get things right or wrong. If you're doing well, if the hypothesis is pretty good and the misclassification penalty is pretty low, then this number is going to be slightly larger than 1, this alpha here. So for each example, change the weight. If the hypothesis got it correct, then that example becomes less important. This is like some positive number, so this becomes a small number, so this makes it smaller. Otherwise, if we got this wrong, then this is a positive number, so that's a positive number, so this gets bigger. So the weight on that example goes up. Normalize the p's to sum to 1, so that we have a probability distribution again. And then go around the loop. And we keep track of h sub t and alpha sub t for every hypothesis we learn. When we come around the loop again, the examples that we got wrong are going to have bigger weights. We're more likely to get them correct. At the end of the day, when at some point we somehow decide when we're going to stop the boosting process, and we return all the hypotheses weighted by their individual alphas. And when we get a new example, you run each classifier and choose a weighted, they each vote, but the strength they get in voting is proportional to how well they classified the examples. So if somebody's weighted misclassification, if someone tended to misclassify, they'd get very low weight. In fact, if they tended to do worse than 0.5, you would weight their vote inverse, so which makes perfect sense, right? If they usually got it wrong, then you would guess the opposite of what they voted about whether the example is in the class or not. Whereas if they did very well, you'd highly weight their vote, exponentially more. So you end up with this weighted voting scheme among all the hypotheses that you've learned. It's a very straightforward algorithm. It's very hard to be sure that it is going to work. And so people have written papers proving properties of this particular algorithm. And it has some amazing properties. So one is that it works. It has a very interesting behavior. So one thing people have noticed is that even after, so I told you that it's proven if you keep running it, you'll eventually get 0 training error. And we saw that in the little applet even. But something even cooler happens. Even after you reach 0 training error, if you keep boosting, your error, your expected error on new data that you see continues to go down. And you may say, okay, how is that possible? That by continuing to train, we could be doing better on held out data. And there's this magical property that boosting has. Certain algorithms have this property, and boosting is one of them. It does something called maximizing the margin, which means that it tries to put its decision boundary right in the middle of the examples. So this is where we need a picture. So if these are the positive examples and these are the negative examples, then I think you'd agree that, oh God, I have to draw a straight line. Terrible at drawing lines. All right, that's a straight line. That gets 100% accuracy on the training data. So, my friends, does this line, right? Right? You've got a lot of latitude about what line, what hypothesis you're going to return, which one to choose. Well, intuitively, we would want to choose the one where the line is as far away from the nearest examples as possible. This distance between the hypothesis and the nearest examples is called the margin, and so a maximum margin learning method is one that tries to choose the hypothesis that maximizes the margin. And you can imagine that if these training examples were randomly chosen, that this is likely to generalize better than either of these other two hypotheses. So boosting has this wonderful technique where it maximizes the margin. So you can even continue to improve after you have zero training error because it continues to adjust this line until it's right in the middle. What do you think, Dan? Cool? You look a little skeptical. I haven't proved it to you, and I'm not going to because I don't know the proof, but someone's proved it.
So each time it changes each classifying line?
No, it learns, once you've learned a classifier, it's fixed. You just keep learning more classifiers.
Okay, so it adds new classifiers which are
to the mix.
Have better margins than the previous.
Well, every time you add a new classifier, you are adjusting the ultimate, what the resulting ensemble classifier is going to do.
So is a classifier just a line?
Well, if your weak learner is a linear learner, you can use anything as your weak learner. In the applet, it was a linear classifier because linear classifiers are awesome, as everyone knows. But it could be anything. But if we take our weak learner as a line, then yeah, you're adding additional lines, and the idea is that the ones near the decision boundary are the ones you're most likely to be getting wrong as you add additional classifiers. So you're going to be adjusting the boundary there, and those examples are going to become very important. So the future classifiers are going to be concentrating on those. Yeah, so that's boosting. Absolutely magical, amazing technique. But only the grad students have to implement it. Now, boosting is not magic. It is magical, but it's not a panacea, I should say. It's not going to solve all of AI for us. You might not have very much training data, and boosting is not going to help you magically create more training data that will get a better idea of what the classes are. If you've only seen 2 chairs in your life, then when someone shows you a stool with a back, I have seen stools with backs on them, and don't tell me they're chairs. They totally are just a stool with a back stuck on. That's a very tricky example. So, yeah, stool with. I never thought about that before. We should totally.
Like a bar stool?
Yeah. There, see? Look. Right? Stool. That is a stool. Don't tell me that's a chair. Those are stools. So says Google, and Google knows everything.
The middle one on the bottom is totally like...
That looks a little bit like a chair, but I don't know.
Where's the dividing line?
Oh, where's the decision boundary? So if you're learning a complex concept, it can be tough. Oh, wow. So you might just not have enough data. Um, if you give boosting a really crappy learner, it's going to take forever and you might not have enough data. If you give boosting a really strong learner, let's see, why is that a problem? Well, because then it gets everything correct right off the bat and you're done. Why is that a problem? I don't know. I don't know. If you don't do boosting, you can have this problem that your hypothesis class is too small. I mean, in essence, boosting by combining classifiers is expanding the hypothesis class that you're exploring, which is a kind of neat idea. Like we just saw with that circle. Like I was using linear classifiers, but we learned a circle out of linear classifiers. So like the space of all ensembles of lines is bigger than the space of lines. In fact, I hear there were even these painters around the turn of the 19th century that made paintings out of dots, right? But by combining lots of dots, you could make shapes. So this is a general problem with machine learning algorithms that you can have if you're not boosting. One wonderful thing about boosting that I forgot to mention is that it can actually identify outliers for you, because those are the ones the examples that are causing problems are going to be weighted highly. So if after a few rounds you have some example that has way more weight than any others, those are the ones that are the classifiers really having problems, and they may well be outliers. So that's very cool. Your machine learning algorithm can be diagnosing problems in your data set for you. So that's nice. And let me tell you, when someone gives you a 200-dimensional data set, finding an outlier, like you can't just look at the data. It's a little hard. So it's nice to have that. That's boosting.